it does work now. Yeah. Okay. So the first time that I heard Raghu's name was in 2007. At that time, I was living in Oslo, which is the city where the Abel Prize is awarded each year, and this year the prize was going to Raghu. So I actually didn't know any probability at the time, but I was interested in math, so I naturally heard about this award. So for this reason, Raghu is actually he's actually the first probabilist that I learned the name of, and I've had a lot of respect for him since that time. For the past 2 years, I've also been so lucky to be his colleague at Courant, and he's been an extremely welcoming colleague for me as a new faculty, and I'm very impressed by how active he still is. So the topic of this talk is actually not so closely related to many of Raghu's works, but there is one particular problem that I will be discussing, which is related to Raghu's work. So this is the general problem of random walk in random environment. The random environment in our setting will be a random planar map. And this random planar map has been embedded in the unit disk. And we're doing a simple random walk on this random planar map. And we can argue that this simple random walk on the random planar map is converging in the scaling limit to a 2D Brownian motion. So this is as the size of the random planar map is going to infinity. So what is a random planar map? A planar map, it is a graph drawn on the sphere, which is viewed without edge crossings, which is viewed modulo continuous deformations. For example, the left and the middle planar maps in this figure, they're considered to be the same, since we can get from one to the other by doing a continuous deformation. The middle and the right planar maps, on the other hand, they are not considered to be the same. So one can get from, so viewed as graphs, these two planar maps are the same, but viewed as maps, they're different because the embedding into the plane is different. So in order to get the right planar map from the middle planar map, then this edge has to be moved here. So why are planar maps interesting? So they are studied in many different branches of both math and physics. The study of planar maps in the math literature goes back to the 60s in the combinatorics literature. So then Tutte, and others were proving enumeration or counting formulas for planar maps. So they're also studied in, for example, geometry and in random matrix theory. A relevant application for this talk is in random geometry, where probabilists are trying to understand the asymptotic properties of large random planar maps. And another relevant application is the conformal field theory and string theory, where planar maps are used as models for random surfaces. So here you can see a large random planar map with a few thousand vertices, which has been embedded into R3. So if one has a large random planar map, then it's typically not possible to embed it in R3 in an isometric way. But this embedding should be viewed as an embedding, which in some sense is as close to isometric as possible. So here I have, so this figure is showing a photo of a 3D printed random planar map. I actually brought this 3D printed random planar map with me to the conference, and I have it here in my hand. It has been made by Maurice Ang, so for those who are interested in having a look, you can come and see me during the next coffee break. In this talk, we will be considering a particular non-uniform probability measure on random planar maps. And to explain this, I need to introduce spanning trees. So here you can see a planar map with a spanning tree T. So this is the subset of edges shown in red. So this is connected without any loops and covering all the vertices. So here you can see one planar map M with two distinct spanning trees, T and T tilde. And we let n of m for some planar map m, we'll let it denote the number of distinct spanning trees of this planar map little m. As for example, for the planar map in the figure, it turns out that it admits 32 different spanning trees, so n of m is equal to 32, and you can see two of these 32 spanning trees in the figure. So here is the random planar map model that we are interested in, and we call them tree-weighted random planar maps. So we sample the random planar map big M in such a way that for any fixed planar map little m of size n, the probability that big M is equal to little m is proportional to n of little m. where we recall the definition of n of m from the previous slide. So equivalently, what we can do is to sample a pair m comma t uniformly at random, where m is a planar map of size n and t is a spanning tree on m. And then we forget the spanning tree and we only keep the planar map m. A natural generalization of this model is explained in the last bullet point. So we let C be some parameter less than or equal to 1. And then we sample a planar map exactly as in the first bullet point, except that on the right side, we have an exponent minus C over 2. So why is this model for random planar maps interesting? So one reason it's interesting is interesting scaling limit conjectures coming from the physics literature, which I will explain on the next slide. Another reason it's interesting is a physics heuristic, which is saying that random planar maps sampled in this way, in some sense, has been reweighted by the number of ways to embed it in a c-dimensional space. So this number n of m is interesting because it is related to a number of statistical physics models on the planar map, for example, the Gaussian free field, and it is also called the Laplacian determinant of m. So this special case when c is equal to minus 2, so this is corresponding to this model that we are primarily interesting, presented in the first 2 bullet points on this slide. So this particular case is particularly, one reason it's particularly interesting is a projection known as the Mullen projection. So this is a projection which was discovered by Mullen between planar maps with a spanning tree and walks on Z2. And you see that this was discovered already in the 60s, which is much earlier than the physics applications discussed higher up on the slide. Yeah. Yeah.
C is negative 2.
Yeah, so it's true. So this is true. So of course, what you're saying, it somehow only makes sense when C is an integer, like a positive integer.
It's the negative sign.
Yeah, but when it is a positive integer, that's.
I'm okay with negative 2.
Yeah. But so as you can see that somehow the model can be defined for any C. And as you can define it for any C, so I guess on this slide I could actually have worked with any C, any real C. The reason I am, and then some of the motivations for introducing this model, or some of the heuristics, was actually this physics heuristic. But then it turns out that the model is actually easier to understand and analyze in the case when C is less than or equal to 1. So these scaling limit conjectures, they're only true when C is less than or equal to 1. So it's actually, so one can also define it for larger C, but then one actually, in the scaling limit, if one takes the scaling limit in the most natural way, one just gets a CRT. I do believe that there are sort of other ways of taking a scaling limit. So if one somehow lets the total number of vertices be free, one can also try to take some kind of scaling limit and then get something non-trivial. So one can also study the model for larger C. Yeah. And this was also some of the origin of the model. So we have this Mullen projection, which is a projection between planar maps with a spanning tree and walks on Z2. On this slide, I want to give an overview of conjectural scaling limit results for this model. So we let M sub n be a random planar map of size n with central charge C, sampled as on the previous slide. So then there's an ansatz from the physics literature known as the DDK ansatz, which is saying that a planar map sampled in this way it should converge as its size goes to infinity to some continuum, a random surface that we call a gamma Liouville quantum gravity surface. So I will be introducing this surface on the next 2 slides. And the ansatz is also saying that the parameter gamma of this LQG surface is related to the parameter C of the planar map model via the formula in the indented equation. So in particular, the case C equals -2 is corresponding to gamma equal to the square root of 2. So then a natural question is what it means that m sub n is converging when its size is going to infinity. So when I say that m sub n is converging to some continuum object, what's the precise mathematical meaning of that statement? And there are actually several different ways that one can formulate convergence results for planar maps to LQG. So the first notion of convergence that one can consider is convergence in metric topology. So the idea here is that we view the planar map as a metric space by equipping it with a graph distance. And then one can show a convergence of this random metric space to some limiting object. So this notion of this topology of convergence is also what we call the Gromov-Hausdorff topology. So second, one can also consider a topology, often called the mating of trees topology. So the idea here is that we are considering some statistical physics model on the random planar map. And we're showing, and one is showing that a particular observable of the statistical physics model is converging as the size of the planar map is going to infinity. So these first two notions of convergence, metric topology and mating of trees topology, so they have been considered in a number of different works. And for a number of different planar map models, one can prove that they do converge in the scaling limit to the LQG in these two topologies. But these results are not going to be the topic of this talk. So in this talk, we will be considering a third notion of convergence known as convergence in conformal topology. So the idea here is that a planar map it defines a surface with some conformal structure, and we're showing convergence of this surface. So we'll explain more precisely what I mean by this a little bit later in the talk. So this is, so now I want to give a brief introduction to the LQG, and in order to do that, I first need to introduce the Gaussian free field. So suppose that D is some domain in the complex plane, so then the Gaussian free field, it can be heuristically defined to be the random function which has been sampled from the measure that you see in the first bullet point. So here d phi is the Bayes measure on the space of real value functions on D, and we are reweighting this by e to the power minus the integral that you can see. So this definition is not making rigorous sense as given, for example, because I haven't explained what this Bayes measure on the space of real valued functions is. However, one can argue that one can make a rigorous sense of some variant of this definition, and it turns out that the resulting object is actually not a random function. So instead it is a random distribution or a random generalized function. So this means that if z is some fixed point in our domain, then h of z is not well defined. However, if f is some smooth test function, then the integral of h against f is well defined, and this will be some random real number. More precisely, one can argue that with probability 1, h is an element in the subbolus space h minus epsilon for any strictly positive epsilon. So one can also argue that H is a Gaussian field, and a Gaussian field which is such that the covariances are blowing up logarithmically when the two points in question are approaching each other. So what is this LQG surface? So a heuristic definition of an LQG surface is to say that it is the random 2D Riemannian manifold where the metric is given by the standard Euclidean metric, locally reweighted by e to the power gamma h, where gamma is some parameter between 0 and 2, and h is a Gaussian free field. So this definition is not making rigorous sense, because h is a distribution and not a function, so it's not obvious what e to the power gamma times h means. However, the area measure associated with this manifold can be defined in a rigorous way. So heuristically speaking, this should be the area measure that has density e to the power gamma h relative to Lebesgue area measure. And this area measure can be defined in a rigorous way via regularization. So we let h sub epsilon be some a regularized version of h, meaning that it is some smooth function approximating h. Then we can use h sub epsilon to define an area measure, and it's possible to argue that this area measure is converging as the regularization parameter epsilon is set to 0 to some limiting area measure mu. So this is the rigorous definition of what we call the Liouville area measure. In the figure, you can see some illustration of this random area measure mu. Heuristically speaking, These red regions correspond to high-density regions where the gas free field is very large, and the blue regions correspond to low-density regions where the GFF is very small. So this random surface model was first introduced by Polyakov in the early 80s in the context of string theory, and in more recent years it has been a very active object of study in probability theory. The study in the probability literature was initiated in the last two works that you see cited on the slide. When gamma is equal to the square root of 8 over 3, then this LQG surface is equivalent to what is called the Brownian surface. So this is actually not something we will be needing in this talk, but I'm mentioning it because probably most of you have heard about Brownian surfaces in other contexts, for example, the Brownian map. So the precise definition of the LQG and the GFF will actually not be needed either in the remainder of the talk. The only object from these slides that will appear later is this random area measure mu. So for the purpose of the rest of the talk, the only thing you need to remember is that Liouville quantum gravity is providing us some natural way of defining a random area measure in a subset of the complex plane. So the next thing I want to do is to explain what I mean by convergence in conformal topology. So I want to elaborate on this notion of convergence that you see in the third bullet point. So in order to explain what it means that a planar map is converging in conformal topology, then the first thing we need to do is to define some discrete conformal embedding of the planar map. So this means that we want to define some function phi on the vertices of the planar map, which takes its value in the sphere, or more generally in some subset of the complex plane. And we want to define this function in such a way that it can be viewed as discrete conformal. So what does it mean that phi is discrete conformal? So before answering this question, I want to answer an easier question, namely if phi is some smooth function between two domains in the complex plane, what does it mean that phi is conformal? And there are actually several equivalent ways to define what a conformal map is. So the most commonly considered definition is probably to say that it is a complex differentiable function with a non-zero derivative everywhere. Equivalently, one can say that it is a real differentiable function which is satisfying the Cauchy-Riemann equations. So one can also get a third definition by using Brownian motion. Brownian motion is what we call conformally invariant, which I've illustrated in the figure. So in the left part of the figure, we have Brownian motion W, and then we consider the image of the Brownian motion W under some conformal map phi. And conformal invariance just means that the image of a Brownian motion under a conformal map still has the law of a Brownian motion, at least modular reparameterization of time. And this property can actually be used to characterize conformal maps. So a smooth orientation preserving projection is conformal if and only if a 2D Brownian motion is sent to a 2D Brownian motion. So one can also use percolation in a similar fashion as 2D Brownian motion. And the fifth way to define it is to use approximation by what we call circle packings. So these are just 5 out of many equivalent definitions of a conformal map. So each of these definitions is giving rise to some natural notion of a discrete conformal embedding. So if one is given some planar map, then different discrete conformal embeddings are typically not identical. However, if one has some large random planar map, then it is believed that the various discrete conformal embeddings will be approximately identical. So next, I want to explain what kind of discrete conformal embedding one is getting if one is using the third definition of a conformal map, namely via Brownian motion. The first thing we need to do is to fix uniquely the conformal map on the previous slide. So here we have a conformal map between a domain D and a domain D tilde. So now we fix the domain D tilde to be equal to the unit disk. We fix a point A in the bulk and a point B on the boundary, and we require that A is sent to 0 and that B is sent to 1. So this is uniquely determining phi. So then we want to define some function phi sub n, which can be viewed as discrete conformal and which is approximating this conformal map phi, which I defined on this slide. And we want to define phi sub n on the graph that you can see in this figure. So this is a rescaled version of Z2 restricted to the domain D. So we want to, so the vertices of this graph are shown in purple and gray, and we want to define this function phi sub n on this graph. You see that some vertices are colored purple and some gray. So the purple vertices are those close to the boundary, and we refer to these as the boundary vertices. And I will first want to explain how we define phi sub n restricted to the boundary. So there's restricted to the boundary, we are defining phi sub n such that the formula in the identity equation is holding. So first we pick some arbitrary boundary vertex v, and then we want to define phi sub n of v, and we define phi sub n of v such that this formula is holding. On the left-hand side of this formula, we're considering a random walk, a simple random walk on our graph, started from the point A, where A is a vertex which is approximating the point A on this slide. And then we are running this simple random walk until it hits the boundary, and we're considering the probability that this simple random walk is hitting the boundary in the boundary arc between the points B and V. On the right-hand side of this equation, we're considering a Brownian motion in the unit disk. This is a Brownian motion z. We run it until it exits the unit disk, and we consider the probability that it exits the unit disk in this boundary arc between the points 1 and phi sub n of v. So if we require that this formula in the identity equation is holding, then this is uniquely characterizing the point phi sub n of v. So then, to define phi sub n in the bulk, we require it to be discrete harmonic. The conformal map phi from the previous slide, since it is conformal, then it follows from the Cauchy-Riemann equations that the real part of phi and the imaginary part of phi are both harmonic. So therefore, we require phi sub n to be what we call discrete harmonic, meaning that it satisfies some variant of the mean value property. So namely, phi sub n of v is equal to the average of phi sub n of w, where we take the average over the 4 neighbors of w. And this property can also be expressed equivalently in terms of random walk. I'm including this equivalent description just to emphasize the close relationship between this embedding and the random walk. So by using conformal invariance of Brownian motion, along with the fact that the simple random walk on Z2 converges in a scaling limit to the Brownian motion, then one can argue that this discrete conformal map phi sub n is converging to the conformal map phi as the lattice size 1 over n is going to 0. So this Tutte embedding, it can actually also be defined for planar maps. So to be more precise, we need to consider planar maps with what we call disk topology. So these are planar maps which have a boundary. So for example, this planar map, it has a boundary given by this purple loop, which is a simple loop and which is enclosing the remainder of the planar map. Here you can see some large random planar map with this topology embedded in R3, and this red curve that you can see, it's actually forming a loop, and this red loop is the boundary of the planar map. And then we can define this embedding. So this embedding I was presenting on this slide is called the Tutte embedding, or harmonic embedding. And this Tutte embedding can also be defined for planar maps. And it is defined exactly as in the lattice case. First, we need to fix a bulk vertex A and a boundary vertex B, which are sent to 0 and 1. Then all the boundary vertices are embedded, so they satisfy this formula. And then all the bulk vertices are embedded, so they satisfy this formula. The resulting embedding for some random planar map is shown here in this figure. It's not difficult to see from the definition that the Tutte embedding is well defined, so it exists and is unique. Once these two fixed vertices, A and B, have been chosen. So when we embed this random planar map in the unit disk via the Tutte embedding, then the planar map will induce a natural area measure in the unit disk, which I denote by phi sub n of v. No, mu sub n. And mu sub n is given by a rescaled vertex counting measure. So each vertex is given mass 1 over n, and then the area assigned to some subset u of the unit disk is equal to the mass of the vertices contained in this set. So it's natural to do this rescaling by n, because n represents the total number of vertices. So with this rescaling, the total area of the unit disk will always be always be equal to 1, even as we send n to infinity. So then, in work in progress, we're proving that that if we consider our tree-weighted planar map and embed them via the Tutte embedding, then this rescaled vertex countermeasure is converging in the scaling limit to a limiting area measure mu. So here we have the random planar map we're considering. It is a tree-weighted random planar map with a topology of a disk. Then we're embedding this planar map in the unit disk via this Tutte embedding. And then we're defining this rescaled vertex counting measure mu sub n, as described on the previous slide. And then we're arguing that this is converging to some limiting measure mu as the number of vertices is going to infinity. And this limiting measure mu is exactly the Liouville quantum gravity area measure that I was presenting earlier in the talk. So it's given by, it's a measure which, heuristically speaking, has density e to the power gamma h relative to Lebesgue area measure. And the value of gamma is equal to the square root of 2, which is consistent with the DDK ansatz, as I was presenting on this slide. So why is this theorem interesting? So one reason it's interesting is because it is a first convergence result under conformal embedding for a non-uniform and combinatorially natural random planar map model. So there have been several earlier works which have been studying random planar maps under conformal embedding. Or to be more precise, there are two series of works. So the first such result was a work by Gwynmiller and Sheffield. So they were considering a particular random planar map model obtained by discretizing LQG. So they were considering an LQG surface. They were discretizing the surface in a natural way, which gave them some planar map model. Then they were considering the Tutte embedding of this planar map, and they were showing that the Tutte embedding of this planar map is converging to the original LQG surface. So this result of Gwynmiller and Sheffield is very nice, and the proof is very innovative. But one downside of the result is that the particular planar map model that they are considering is not so combinatorially natural, because it is obtained by starting with a continuum object and discretizing it. So then, in another work with Shin Sun, we were considering uniformly sampled planar maps, and we were showing convergence under these uniformly sampled planar maps under what we call the Cardy-Smirnov embedding. So this is a conformal embedding which is based on percolation. So it is so this Cardy-Smirnov embedding. It's using the fourth definition of a conformal map as given on this slide in a similar fashion as a random walk, and as a similar fashion as the 2D random motion is used in for the third definition. Or this embedding is using percolation in a similar fashion as the random walk was used to define the Tutte embedding. And this embedding, it could be argued to be discrete conformal by using a Smirnov's proof of Cardy's formula. Yeah.
So your theorem here is for C -2,
yeah,
is
yeah.
gamma square root.
Yeah, yeah.
But you expect it to be valid for all range of C's and gammas? Or?
Yeah, yeah. And the proof technique should, in principle, also generalize to other values. Well, to be more precise, it should generalize to not necessarily exactly this model, but for models in the same universality class. So one can get a range of gamma values, but the discrete model is defined in a slightly different manner as exactly what I was presenting. So yeah, I can elaborate a bit more on this. What were you saying?
Why isn't this defined, just changing the C?
So the result should be true. I didn't entirely hear the question, but so the thing is that the result should be true for arbitrary C, and then so this proof is only for C equals -2. And then, so I will say a few words about the proof technique. So the proof technique, it doesn't, so it also, in principle, should work for C equals 0. And then for other values of C, then it should be, then it's not exactly the same discrete model that I was defining earlier, so maybe I can explain this. So it should be, so here I'm defining this particular random planar map model. So instead of putting this particular thing on the right-hand side, one could in principle put the partition function of a statistical physics model, which is believed to be asymptotically the same. And for certain such statistical physics models, one can also hope to carry through the proof, but it's but this will actually not be for this precise model. Yeah. Okay, so. So as a byproduct of the proof, then I'm coming back to this problem that I was discussing at the very beginning of the talk. We're getting that a simple random walk on this planar map is converging in the scaling limit to the 2D Brownian motion. So here in the figure, we're considering the tree-weighted random planar map embedded via the Tutte embedding. And we're doing the simple random walk on this random planar map, and this will converge in the scaling limit to a 2D Brownian motion. So one particular difficulty of considering random walk in this particular random environment is the fact that the random environment is very inhomogeneous. So you can see that there are certain parts of the disk where the density of vertices is very, very high, and certain parts of the disk where the density of vertices is very, very low. And this is one of the key difficulties in understanding random walk in these types of environments. In the remaining time, I want to say a few words about the proof. I don't know how much time do I have left? 8 minutes, okay, yeah. The starting point of the proof is the Mullen projection. So this is a projection between planar maps with spanning trees and walks on Z2. And this projection is such that the size of the planar map is corresponding to the length of the walk. So if one has some random walk on Z2, then it will converge in the scaling limit to the 2D Brownian motion. And on the continuum side, then one has a similar relationship where a 2D Brownian motion is encoding a level quantum gravity surface. So this encoding was discovered by Duplantier, Miller, and Sheffield, and this encoding is some continuum version of the discrete projection. So suppose now that we are considering our random walk on Z2, and we have coupled it with a 2D Brownian motion. So then this is giving us some natural embedding of the planar map, which I denote by phi tilde, and it is defined by the formula that you see in the first bullet point. In the Mullen projection, it is the case that each vertex v of the planar map, it corresponds to some time t sub v for the walk. On the continuum side, each time t for the Brownian motion, it corresponds to some point p of t in the unit disk. So for this reason, it's natural to define an embedding of the planar map where some vertex v is sent to the point p of t sub v in the unit disk. So then, in order to prove the theorem on this slide, then it turns out that it is sufficient to prove that this embedding phi tilde is approximately equal to the Tutte embedding. So I will not explain exactly why this is sufficient, but essentially it follows by using properties of all the relationships that are displayed in this diagram. So in order to prove that phi tilde is approximately equal to the Tutte embedding, then it is again sufficient to argue that the simple random walk on the phi tilde embedded random planar map is converging to the 2D Brownian motion. So the figure you see here, you can view it as some schematic drawing of this phi tilde embedded random planar map, and we're doing a simple random walk on this random planar map, and we need to argue that the simple random walk is converging to the 2D Brownian motion in the scaling limit. To prove this, then we are applying an invariance principle due to Gwynn, Miller, and Sheffield. And this invariance principle was actually also playing an important role in the proof in the result of Windmiller-Sheffield as presented on this slide. So Windmiller and Sheffield, they were considering random walk in a particular random environment, and they were proving that under certain assumptions on the random environment, then the random walk will converge to the 2D Brownian motion. So before commenting more on the assumptions of this theorem, then I want to explain what kind of environment that we will apply this theorem to. So the environment that we will be applying the theorem to is a particular local limit of the phi tilde embedded random planar map. So in the left part of the figure, we have a phi tilde embedded random planar map. Then we're sampling a point from the Lebesgue area measure in the unit disk, and we're zooming in nearby this point. And it's possible to argue that if we zoom in at the same time as the size of the planar map is going to infinity, then what we're seeing is having a local limit in law. So this local limit in law will look something similar to what you see here, which is some infinite random planar map, which is embedded in the full complex plane. And this local limit is the random environment that we will be applying this invariance principle to. So in order to apply this invariant principle, then we need that our graph is well connected, meaning that the number of edges that the density of edges is sufficiently high. We need that it's ergodic. We need that there are not too many long edges, and we also need that there are not too many high-degree vertices. But the thing about this invariance principle of Windmiller and Sheffield, which is probably making it stand apart the most from most other invariance principles, is an assumption, which is that the environment is translation invariant modulo scaling. So there are a number of invariance principles in early literature, which is requiring the environment to be translation invariant. But they are replacing this with some weaker property. So they are requiring that if we are translating the environment, then the translated environment has the same law as the original environment after we have applied some possibly random scaling. So it is exactly the same as traditional translation invariance, except that we're also allowed to do this random scaling of the environment. And then it's possible to argue that this local limit is satisfying the assumptions of the Windmiller-Sheffield theorem. So what is the difficulty of the proof? So the difficulty is to argue that this local limit exists, and also to argue that the properties of the Windmiller-Sheffield theorem is satisfied. So even proving that this local limit exists is a very hard problem. And the reason it's hard is that you see that in order to define phi tilde, we need to have some coupling between the walk and the 2D Brownian motion. When taking the local limit, we also need to take some kind of local limit in this coupling. So we need to have we are given some random time for the 2D Brownian motion and the random walk, and we need to take a local limit at this random time. And the issue is that this random time, it's having a very complicated law, and it's coupled together with the 2D Brownian motion in a complicated way, which makes it very hard to prove that this local limit even exists. But it is possible to argue that it does exist, and one can also argue that it satisfies these other criteria of the theorem, of the invariance principle. And one key tool which is being used in the proof is a strong coupling of 2D random walk and 2D Brownian motion. Okay, thanks.